Okay, continuing the sample problems for Chem 111. This time we're talking about stoichiometry and stoichiometry related to limiting reagents. So, first example. Ammonia will react with fluorine to produce dinitrogen tetrafluoride and hydrogen fluoride used in the production of aluminum, in uranium processing, and in frosting of light bulbs. How many moles of ammonia are needed to completely react with 13.6 moles of fluorine? So the first thing we have to do is, with all of these, is write a balanced chemical reaction. So ammonia, which is NH3, is reacting with fluorine, F2, to produce dinitrogen tetrafluoride into F5 and hydrogen fluoride, which is HF. Right? So we have to balance this. So if we start with the nitrogen, here we have one nitrogen here, two nitrogens over here, so we need a 2 there. If we look then at hydrogens, we have a total of 6 hydrogens on this side, 1 hydrogen on that side, so we need to put a 6 there. And then the only thing left we have is the fluorine. So we have 2 fluorines here, 5 fluorines plus 6 fluorines. Oh, made a mistake already. Tetrafluoride, this is a 4, excuse me. So 2 fluorines and 10 fluorines, so we have to make this 5. Right? So this is our balanced chemical reaction. Right? So that means for every 2 moles of ammonia we react, we need to we will have to also have 5 moles of F2 present. So if we want to know how many moles of ammonia are needed to react this fluorine, we're going to start with this 13.6 moles of F2, and then from the balanced chemical equation, for every 5 moles of F2 we react, we need to have 2 moles of NH3. Right? So 13.6 times 2 divided by 5 gives us 5.44 moles of NH3 is needed. Right? A fairly simple, this one we're only working in moles, but we still have to balance the chemical reaction. And you can see that we can do stoichiometry in this example on the 2 reactants, not only converting between reactants and products. All right, let's look at another one. How many grams of sodium fluoride used in the water fluorination and manufacture of insecticide are needed to form 485 grams of sulfur tetrafluoride? All right. If we have this reaction, 3SCl2 plus 4 sodium or NaF gives us sulfur hexafluoride plus disulfur dichloride plus sodium chloride. So the first thing we should do is make sure that this is balanced. So we have 3 fluorines on this side, 3 fluorines on, or excuse me, sulfurs, 3 sulfurs, 6 chlorines, 6 chlorines, 4 sodiums, 4 sodiums, 4 fluorines, 4 fluorines. So this is in fact balanced. I would always suggest that you check to make sure it's balanced, just in case for those few times that it's not, even though it appears to be balanced at the beginning. Right? So we want to calculate the mass of sodium fluoride. So we want the amount of this that had reacted if we formed a certain amount of sulfur tetrafluoride. Right? So our plan is we're going to start with the mass of sulfur tetrafluoride, convert that to moles, because the balanced chemical reaction deals with moles. From moles of sulfur tetrafluoride, we're going to figure out how many moles of sodium fluoride we had to react. And then we wanted a mass, so we have to then convert to grams of sodium fluoride. Right? To do the mass to mole conversions, we're going to use the molecular mass or molar mass. To do the mole to mole conversions, we're going to use our balanced chemical reaction. So if we form 485 grams of sodium or sulfur tetrafluoride, we know that we have 1 mole of sulfur tetrafluoride if we have 70.07 grams of sulfur tetrafluoride. Okay. So now our masses cancel, we're left with moles. We're at this step. And then we need the molar-molar ratio to go to the sodium fluoride. So from the balanced equation, for every 1 mole of sulfur tetrafluoride that we produce, we had to react 4 moles of sodium fluoride. Right? The answer asks us to calculate grams, so then we have to go through the molar mass again. For every 1 mole of sodium fluoride, we have to react, or we have a mass of 41.99 grams. Again, this mass and this mass we get from the molar mass from the periodic table. And we're left, if we do this, multiply everything on top, divide everything on bottom, we get 1162.6 grams of sodium fluoride. Right? But we have to then, as always, look about significant digits. We're given 3 significant digits here. All the rest of these are conversions, so they don't count towards our final answer. So then we have to round this to 3 significant digits, which would be 1.62 times 10 to the third grams of sodium fluoride. Right? So this would be the amount that we need to react. Next one, aluminum metal reacts with chlorine gas to form solid aluminum trichloride, AlCl3. What mass of chlorine gas is needed to completely react with 163 grams of aluminum? So again, as always, let's start with a balanced chemical equation. We have aluminum is reacting with chlorine gas. Chlorine is one of the diatomic species, so it's going to exist as Cl2. Sodium metal is a solid. This is a gas. If we want to include the states, we can. To form solid aluminum chloride, AlCl3, and it's a solid. Right. We have to then go through and balance this. So we have 3 and 2 chlorines on this side, 3 on this side, so we need to make that a even number, so we'll put a 2 there, which gives us 6, which means we need a 3 there. Go back with aluminum, we have to have a 2 there. Again, balanced chemical equation. So now we're going to look, so we have to, our plan again is going to be to go from aluminum as a mass, grams of aluminum, to moles of aluminum, to moles of aluminum trichloride, to mass or grams of aluminum trichloride. Right? Same sort of plan we had before, we're just using different values. Right, so 163 grams of aluminum, convert from mass to moles. So 1 mole of aluminum has a mass of 26.98 grams. Right. Mole to mole ratio, so from the balanced chemical equation, for every 2 moles of aluminum react, we get 2 moles of aluminum chloride. So now we're here. We want the mass, so we have to then use the molar mass again. So for every 1 mole of aluminum trichloride, we have a mass of 70.9 grams of aluminum trichloride. So this gives us a mass, again, with significant digits. We have 3 here, so we want our final answer to have 3 significant digits, so it's going to be 642 grams. So that's all right. Look at me. I solved for the, this is not the right answer because I solved in this equation for aluminum chloride. We wanted chlorine gas. So that means we have to go back to here. So this isn't right. So 163 grams of aluminum. Again, moles of aluminum. Gives us 26.98 grams of aluminum. Now we want to actually go to chlorine gas. So for every 2 moles of aluminum that react, we have to react that with 3 moles of chlorine gas. And for every 1 mole of chlorine gas, that has a mass of 70.9 grams of chlorine, which gives us a mass of 642 grams. Cl2. Right. So it's the same process, just got to actually read the problem. All right, next, aluminum oxide used as an absorbent or a catalyst for organic reactions forms when aluminum reacts with oxygen. In this reaction, 4Al plus 3O2 gives us 2Al2O3. Again, check to make sure it's balanced. 4 aluminums, 6 oxygens, 6 oxygens. A mixture of 82.49 grams of aluminum and 117.65 grams of oxygen is allowed to react. What mass of aluminum oxide can be formed? Now, if we look at this, up until this point, all of the problems we've done have only given us 1 mass. Right? This one gives us 2, which is an indication this is a limiting reagent problem. Right? One of these is going to determine how much of that is formed, because one of them is going to be completely consumed, and once its amount goes to 0, the reaction is going to stop. So the best way to actually solve for this is pretend that we only have one of these at a time. So we're going to do the same calculation that we've been doing once, assuming that this is the only thing that's there. How much of the answer are we going to get? And then assume that we only have this one there. How much of that are we going to get? And then the correct answer is going to be the smallest one. So, again, if we have 82.49 grams of aluminum, we want to figure out how much of this we can form. All right. So, we're going to take 1 mole of aluminum, has a mass of 26.98 grams of aluminum. And from the balance reaction, for every 4 moles of aluminum react, we get 2 moles of aluminum oxide. We don't want moles, though. We want a mass, so then we have to convert to the mass. So moles, for every 1 mole of aluminum oxide, we're going to have a mass of 101.96 grams. So this is going to give us a value of 155.9 grams. Right? 4 significant digits here, 4 significant digits there. We're going to repeat this for the other one. 117.65 grams of O2. Again, repeat the same process. If we have grams, we have to convert to moles. So for every 32.00 grams of O2, we get 1 mole. Right? We want to go to this, so the mole to mole ratio. For every 3 moles of O2 that we react, we get 2 moles of aluminum oxide. And again, we want a mass, so we get 101.96 grams of aluminum oxide for every 1 mole of aluminum oxide that is formed. So now, again, we have 5 significant digits here, so we should have 5 significant digits in the answer. So 249.91 grams of aluminum oxide, as opposed to 155.9 grams of aluminum oxide is this. Right? So if we only had this amount of aluminum, we should get 155.9 grams of aluminum oxide. If we have this amount of oxygen, we should be able to form 249.91 grams of aluminum oxide. Right? We're only going to be able to produce the smallest amount. So the actual answer is going to be the 155.9, because that's going to limit the amount of product that we form. So the amount we form is this 155.9, which makes aluminum the limiting reagent. And oxygen is the excess reagent. Let's do another one of those. So magnesium reacts with iron 3 chloride to form magnesium chloride, which can be used in fireproofing wood and in disinfectants. So we're producing magnesium chloride and iron in this reaction. Again, check it with balance. It is, right? So a mixture of 41 grams of magnesium and 175 grams of aluminum, aluminum's on my mind today, of iron 3 chloride is allowed to react. What mass of magnesium chloride is formed? Right? Again, we have both reactants present, so this is again a limiting reagent problem. But again, we're going to solve it the same way. We're going to say, okay, we want to know how much magnesium chloride is formed. So let's say if we convert all of this magnesium to magnesium chloride, what mass would we have? And if we converted all of this iron 3 chloride to magnesium chloride, what mass would we have? And then we're going to select the smallest one. So let's start with the magnesium, 41.0 grams of magnesium. I'm going to go from grams to moles, moles to moles, moles to mass. So from the periodic table, 1 mole of magnesium has a mass of 24.31 grams. And then for every 3 moles of magnesium we react, we're going to form 3 moles of magnesium chloride. And then for every 1 mole of magnesium chloride we produce, that's going to have a mass of 95.21 grams of magnesium chloride. So if we do this, we're going to find we get 160 decimal grams of magnesium chloride. 3 significant digits, 3 significant digits. Right? Repeat that process again with this one, 175 grams of iron 3 chloride. Convert to moles. So 162.2 grams of iron chloride, 3 chloride, for every 1 mole of iron 3 chloride. From the balance reaction, for every 2 moles of iron 3 chloride we react, we get 3 moles of magnesium chloride. And for every 1 mole of magnesium chloride we form, we get a mass of 95.21 grams of magnesium chloride. Again, units cancel, so we're left with grams. So we end up with 154, again, 3 significant figures here. We need 3 significant figures there, grams of magnesium chloride. Again, the limiting reagent, we're only going to be able to form the smallest amount, which is this 154 grams of magnesium chloride. So that is the amount that we're going to be formed, which makes this iron 3 chloride the limiting reagent. And finally, let's do one more of those. So we have tetraphosphorus hexaoxide is formed by the reaction of phosphorus and oxygen. In this reaction, elemental form of phosphorus, remember, is P4. Oxygen is O2 to form this P4O6. Again, make sure it's balanced. It is. But mixture of 100 and excuse me, a mixture of 75.3 grams of phosphorus and 38.7 grams of oxygen produce 43.3 grams of tetraphosphorus hexaoxide. What is the percent yield of this reaction? Right? So this is a new sort of concept. The percent yield is going to be equal to the actual amount that we formed, right? This 43.3 grams, divided what we should in theory form, or the theoretical yield, right? Which we will have to solve for using stoichiometry, times 100. So what we've given this actual yield, we have to actually calculate the theoretical yield. Based on these two values, what amount of tetraphosphorus hexaoxide should be formed, right? Again, we're given the 2 reactants, so this is a limiting reagent problem again. And we're going to attack it just like we have the previous examples, where we solve for how much can this form, how much can this form. The smaller amount is the amount that's actually going to be formed, which is our theoretical yield. So 75.3 grams of P4, convert to moles, so 123.88 grams of P4, the molar mass, for every 1 mole of P4. From the balanced chemical reaction, from every 1 mole of P4 we react, we get 1 mole of tetraphosphorus hexaoxide. We want a mass. So for every 1 mole of P4O6, we have 219.88 grams P4O6. So theoretically, if we only had this amount, we should be able to produce 133.65 grams of P4O6. So this is a theoretical yield based on this amount. Right? We can also calculate a theoretical yield based on the O2, where, again, convert to moles. So for every 32.00 grams of O2, we get 1 mole of O2. From the balanced chemical reaction, for every 3 moles of O2 we react, we get 1 mole of P4O6. And just like before, for every 1 mole of P4O6, we have 219.88 grams P4O6. Right? So this gives us this value, which when we solve for it is 88.6 grams of P4O6. So this is the theoretical yield based on this amount. Based on the mixture, the theoretical yield is going to be the smaller amount, the limiting reagent result. So this value, this is the smaller amount, so this is the amount that's going to be produced, which is the theoretical yield for this reaction under these conditions. So to calculate our percent yield, we're going to take our actual 43.3 grams divided by what we should get in theory, 88.6 grams, times 100 to give us a theoretical, or percent yield, excuse me, of 48.9%. Right? So in this process, we're going to calculate the theoretical yield based on this limiting reagent, the smallest one that can be produced, divide that into what we actually produce, multiply it by 100 to get a percent.